The performance of local AI inference is rarely gated by pure compute power or flops. The constraint is memory bandwidth and capacity. Loading a 70 billion parameter model requires roughly 48 gigabytes of VRAM dedicated strictly to the weights before the system processes a single word. This diagram maps VRAM consumption during inference. The block filling the capacity gauge is the key value cache. It scales linearly with context length. Pushing the context window from 8,000 to 100,000 tokens rapidly consumes whatever VRAM remains. Standard scalar quantization effectively shrinks model weights, but applying those same compression methods to the KV cache causes the data lines to turn jagged. The model suffers catastrophic coherence loss at extended contexts. The inability to compress the KV cache while maintaining attention accuracy keeps complex, long-context LLM deployment firmly tethered to data centers. Google Research recently published an algorithm called TurboQuant. It compressed the KV cache to 3.5 bits per value, with zero measurable loss in perplexity at context lengths up to 100,000 tokens. Traditional quantization methods like GPTQ or AWQ require data-dependent calibration runs to map out their compression grids based on expected inputs. A grid tuned via calibration on conversational English degrades heavily when processing complex medical records, dense Python code, or financial transcripts. TurboQuant is entirely data-oblivious. It bypasses heuristic calibration completely, processing all incoming tokens using pure geometric transformations. Achieving a 6 times memory reduction across all data domains requires altering the underlying geometry of the vectors rather than forcing them into rigid grids. The mathematical obstacle preventing clean quantization is a property within LLM vector embeddings known as quasi-sparsity. In a vector embedding, a tiny fraction of dimensions carry disproportionate magnitude, spiking 100 times higher than the baseline. When fixed precision quantization grids scale to accommodate these extreme spikes, they waste vital bit depth. The lowest grid segment swallows the smaller bars, destroying their fidelity. TurboQuant first multiplies the vector by a random orthogonal rotation matrix before compression. Orthogonal rotations perfectly preserve geometric properties like distances and angles. By rotating the vector, extreme spikes melt down, distributing energy evenly across the entire axis. The vector's coordinates now follow a tightly concentrated beta distribution. With the energy distributed evenly, optimal scalar quantizers wrap tightly around the distribution, capturing each coordinate independently with maximum fidelity. Mathematically rotating the vector's energy eliminates the need for calibration datasets. The algorithm alters data to fit the grid, rather than tuning the grid to the data. Outliers that break quantization often stem from a specific architectural standard, rotary position embeddings, or ROPE. ROPE encodes positional data by rotating dimension pairs on a Cartesian plane, based on a token's position. Plotted separately, the x and y values form wildly oscillating waves. In Cartesian space, this pure rotation creates the illusion of chaotic, extreme outliers to a quantizer. TurboQuant's second step, PolarQuant, moves KV cache vectors into a polar coordinate system, representing data strictly by a radius and an angle. The radius forms a flat line for magnitude, while the angle forms a smooth slope capturing positional rotation. Standard Cartesian quantization requires storing dedicated per-block normalization metadata, scaling factors, and 0 points just to handle the illusion of those rotational spikes. Aligning the coordinate system to the data's natural geometry strips away the need for normalization metadata, saving 2 bits of critical overhead per value. PolarQuant minimizes mean-squared error effectively, but it leaves a mathematical vulnerability. Mean-squared error optimal quantizers introduce a systematic statistical bias into inner product estimations. This isolates the self-attention mechanism, which calculates scores through inner dot products of query vectors colliding with quantized key vectors. At 80,000 tokens, systematic error accumulates. The attention mechanism drifts, and the model confidently hallucinates. TurboQuant executes a final correction stage by isolating the residual error, the precise mathematical difference between the original 16-bit vector and the PolarQuant compressed vector. The algorithm processes this error through the quantized Johnson-London-Strauss transform, or QJL. It aggressively reduces residual error to a single bit per coordinate, positive or negative. Injecting this unbiased estimator snaps the calculation back to a flat, zero expectation baseline. Combining polar quant's geometric compression with QJL statistical bias correction creates an attention mechanism that matches 16-bit expectations precisely, regardless of context length. Theoretical math requires rigorous testing on live deployments. When the open-source community ran these algorithms on modern architectures like the Quen model families, they hit a barrier. The empirical profiling revealed a massive norm disparity between key vectors and value vectors. This chart contrasts the two distributions. On models like Quen 2.5, the average key vector norm sits at roughly 778. The value vector norm is only 4.3. Quantization error scales with the square of the norm. Forcing a uniform 3-bit compression across both vectors destroys the keys, resulting in a 78% spike in perplexity. The engineering fix for these architectures requires asymmetric bit allocation. By allocating 6 bits to the volatile keys and 3 bits to the steady values, developers preserve the exact 16-bit baseline quality while maintaining massive overall compression. The algorithms are data-oblivious, but the integration is not. Engineers must profile the specific key-value norm ratio of their target architecture before deployment. TurboQuant functionally releases the VRAM handbrake. Local systems previously capped at 8,000 token summaries can now parse 32,000 token legal documents natively in memory. By utilizing custom fused kernels on an H100 GPU, the 4-bit implementation delivers an 8x speedup on raw attention computation. Because the initial rotation is data-oblivious, vector database indexing requires zero dataset-specific training. Build times drop to near zero. The memory wall was broken without waiting for denser silicon or purchasing larger GPU clusters. The efficiency of local inference scales by abandoning rigid compression grids and aligning the algorithms to the natural geometry of high-dimensional space.